right, Chemistry 1411, we're still on chapter 13.3 here. This is question 24 from the slides. A 4-liter flask at equilibrium contains 0.2 moles of N2O4 and 1.6 moles of NO2 and reacts according to the following reversible reaction that we have shown here. 1 mole of N2O4 is in equilibrium with 2 moles of NO2. The volume of the container is then increased to 8 liters. How many moles of each gas will be present when the new equilibrium is reached? And so I'm going to go a little faster than I have on some of the previous problems. And I think the first thing we should do here is they tell us we're at equilibrium and they give us the number of moles in the volume of the flask. So we can figure out what our Kc is. Kc is going to be concentration of NO2 squared divided by concentration of N2O4. They've given us the number of moles of the NO2, which is 1.60 moles. The flask has a volume of 4 liters, and we're going to square all that, and we're going to divide that by the concentration of our N2O4, which is 0.200 moles per 4 liters. There you go. And when you do that calculation, you get the Kc when we're at equilibrium is 3.20. So there's our K value. And so now what we're going to do is we're going to increase the volume from 4 liters to 8 liters. And so when we increase the volume, it's going to change the concentration, the initial concentration of the dinitrogen tetroxide, the N2O4, and the NO2. So I'll put here volume increased to 8.00 liters. And so when we do that, our new concentration of N2O4 is going to be equal to the 0.200 moles, but now I'm in 8.00 liters, and that gives me a concentration of 0.0250 molar, and the concentration of my NO2 is going to be 1.60 moles divided by 8.00 liters, and that gives me 0.200 molar. And so if we take a look at our equilibrium, it's going to look like this, where we have our N2O4 in equilibrium with our 2 moles of NO2. And now we've changed things up. We've changed the concentration of our N2O4 to 0.0250 molar. And we've changed the concentration of the NO2 when we increase the size of the flask to 0.2 moles per liter. And so our question is, which direction is the equilibrium going to shift? Well, we've increased the size of the container. And so we know that the side that has the 2 moles of gas is going to take up more space than the side that has 1 mole of gas, right? So here we have 2 moles of gas. Here we have 1 mole of gas. So that means this side is going to take up less space, and this side is going to take up more space. And so if we've increased the size of the flask, that means the equilibrium is going to go to the side of the products. And so we can write for a change, we can write subtract x, and here we can, and here, since we have 2 moles of gas, we're going to add 2x, right? Because we have a stoichiometric coefficient of 2. And that's the equilibrium. Here we have 0.0250 minus x, and here we have 0.200 plus 2x. All right, so now that we have all that set up, we could set up our K expression. And so we can take this concentration for my N2O4, this concentration for my NO2, and we can plug that into our Kc expression, just like we used above, except now we're going to have our 0.200 plus 2x, and we're going to square all that, divided by our 0.0250 minus x, like that. And we know that all of that is going to be equal to 3.20. And so we can see here that we're going to have to solve a quadratic. And so we're going to have to take this whole thing here, and we're going to have to solve for x. So solve for x. And this, again, is going to involve a quadratic. And so we're going to have to put this equation in the form of ax squared plus bx plus c is equal to 0. So we've got to do that first. Okay, so I've moved the equation over here, and I have the formula for the quadratic equation put here, and we're going to solve for x. And so when we simplify the equation that's in the blue box here, and we put it in the form of ax squared plus bx plus c is equal to 0. When I first simplified it just by multiplying the 0.25 by 3.2, and we end up with, so when we do that, we end up with 0.0800, and then I'm going to multiply the negative x by the 3.20, and so that would give me negative 3.20x. And next, when I square the numerator, so when I square my numerator, I end up with 0.0400, so that's 0.2 times 0.2. And then I take 0.2 times 2x, that gives me 0.4x, and that happens twice. So I'll put 0.0800x, and then 2x squared gives me 4x squared, like that. And so then I just simplify this to 4x squared plus 4.00x minus 0.0400 is equal to 0. And so here I have my A, which is 4. I have my B, which is also 4. And then I have my C value, which is negative 0.04. And I plug that into my quadratic formula. And when you do that, you end up with x is equal to 0.000990 molar, like that. And now if I borrow this from the previous slide, I have what my x value is. And so all I have to do is substitute it into here to figure out the concentration of my N2O4. I do that. I get my concentration of N2O4 is equal to 0.0151 molar. And I do the same thing. I put in my x here, and that gives me the concentration of my NO2. And when I do that, I get the concentration of my NO2 is equal to 0.220 molar, like that. And so now if I want to figure out how many moles of each one of these I have, all I have to do is, since I know that these represent moles per liter, I just multiply it by 8.00 liters. Same thing for the other one. I have moles per, oops, I should have put M. OL per liter. I multiply that by 8.00 liters. And for my N2O4, I end up with 0. And for my N2O4, I end up with 0.120 moles. And for my NO2, when I multiply this out, I end up with 1.76 moles. And so again, you should be able to do the algebra to get from here, okay, to here. You should be able to do that algebra, okay, in Chemistry 1411. So if you need to go back and review some of your algebra, that might be a good idea. But again, you should be able to do that to put all of this, okay, into the form of ax squared plus bx plus c is equal to 0. And then, of course, you need to be able to solve the quadratic.